And we're very happy to have Amy here to tell us about NSDI work on Flexplane. Amy is a student at MIT with Harry Krishnan. So, welcome.
Thank you. So I'm Amy. Today I'm going to talk about Flexplane, an experimentation platform for resource management in data centers. This work was done with Hari Balakrishnan and Jonathan Perry at MIT and Peter Lopkov at Facebook. And please feel free to interrupt me if you have questions at any point. Data center applications today have diverse requirements from the underlying network. Some applications want low latency, while others want high throughput. Others care about fairness, isolation, or meeting deadlines. And these properties can significantly impact the performance of data center applications. As a result, researchers have developed dozens of new resource management schemes for data center networks. These schemes operate in routers in the network and control which packets are sent or dropped and the order in which packets are transmitted. For example, DC-TCP provides low latency and high throughput. PDQ, RCP, pFabric, and PER all attempt to minimize flow completion time. And DCube and deadline-aware data center TCP attempt to meet deadlines. All of these schemes promise significant benefits for data center applications. However, in practice, it's very difficult to experiment with and to deploy these schemes in real networks. This is because most of these schemes require modification to hardware routers, and developing new ASICs for routers is expensive and time-consuming. Instead, researchers have developed a couple of approaches to experimenting with resource management schemes without deploying new hardware. In real networks, some researchers have used programmable hardware such as FPGAs or programmable chips to enable experimentation at line rate. But to date, these approaches really provide limited flexibility, and they require that your network is outfitted with the appropriate hardware in order for you to take advantage of them. Other researchers have used software routers, such as Click, to experiment with new resource management schemes, replacing each hardware router in the network with a server, and implementing their schemes in software there. However, to date, software routers have provided limited throughput of only a few dozen gigabits per second, restricting experiments to only a few servers. Finally, emulation platforms such as ModelNet use one or more servers to emulate an entire target network topology. However, in these approaches, the emulated network throughput is still limited to the aggregate throughput of the servers used to conduct the emulation. The result of these challenges is that most experimentation with resource management schemes today is conducted using network simulators, such as NS. Unfortunately, software simulations don't fully capture the behavior of resource management schemes. First, they don't accurately model NIC features and network stack optimizations, such as interrupt coalescing, which can significantly impact protocol behavior. Second, they don't enable experimentation with real distributed applications, such as Spark or Hadoop, whose performance depend on other resources besides the network, such as disk or CPU. And finally, as anyone who's actually run an experiment using one of these simulations knows, simulations are incredibly slow. Simulating only 1 second of time in a network can take hours. This slows down experimentation considerably. What this means is that no existing approach to experimentation with resource management schemes today provides flexibility, accuracy, and high throughput. This makes it difficult to prototype new reads and to evaluate the performance of existing applications under different resources. In this talk, we make 2 contributions. First, I will describe the key idea of whole network emulation. We emulate the behavior of the entire network, including the resource management scheme and a centralized software emulator, but then send packets over the real hardware network. Second, I'll describe Flexplane, a system that uses whole network emulation to enable users to faithfully experiment with resource management schemes on real data center networks. Flexplane provides 3 main properties. First, it is accurate, meaning that results achieved in Flexplane predict those achieved on real hardware. Second, it is flexible, enabling users to experiment with arbitrary schemes. In Flexplane, users implement their schemes in C++. And finally, Flexplane provides high throughput. Our emulator prototype supports 761 gigabits per second of aggregate network throughput. In Flexplane, we implement the programmable data plane off-path. To achieve this, we augment the network with a software entity called the emulator, which emulates the behavior of the network in real time. The emulator maintains a model of the network topology in software, and users implement their schemes in the emulated routers. Before each packet is sent on the real network, a corresponding emulated packet traverses the emulated network and experiences the behavior specified by the resource management scheme there. So how exactly does this work? When an endpoint sends a packet, Flexplane intercepts it before it is sent out onto the NIC and constructs an abstract packet. An abstract packet is a concise description of the packet. It includes the source, destination, and any other header fields needed by the resource management scheme. The endpoint sends this abstract packet to the emulator. Next, the emulator emulates the behavior of the network under the desired scheme in real time. It maintains an emulated network of routers and endpoints in software, configured in the same topology and with the same routing policies as the real network. Abstract packets begin at emulated sources and flow through the emulated network, encountering queuing delays and modifications such as ECN marks, as specified by the program resource management scheme. Abstract packets can also be dropped in the emulated network. Yeah.
So this emulator is running on some other server connected to the network?
Yeah.
I see. Okay.
Yeah. Once an abstract packet arrives at its emulated destination, the emulator instructs the real endpoint to send the corresponding real packet immediately. If the abstract packet acquired any modifications, such as ECN marks, during emulation, the endpoint applies these modifications to the real packet before sending it. This ensures that the real packet arrives at its destination with the modifications that it would have in a real network that supported the scheme. If the abstract packet was dropped in emulation, the endpoint will drop the corresponding real packet instead of sending it. Because the emulator enforces bandwidth constraints, there will be sufficient bandwidth in the real network to transmit all admitted packets to their destinations. When the real packet traverses the real network, it encounters almost no queuing and no modifications, so higher layer protocols perceive that the packet is queued and modified by the resource management scheme implemented in software in the emulator. In the next several slides, I'll describe the design of Flexplane in more detail and analyze its accuracy. Then I'll describe its implementation and evaluation. The reason that emulation over abstract packets works is that most resource management schemes are data independent, meaning that they don't depend on the packet payload. They depend only on a small number of header fields, which typically comprise less than 1% of the total size of the packet. Thus, the bandwidth required into and out of the emulator is only a small fraction of the total bandwidth supported by the real network. Each abstract packet is a concise description of 1 MTU worth of data. In this talk, an abstract packet represents 1,500 bytes of data. To simplify emulation, all abstract packets represent the same amount of data. This can consist of one large packet or several smaller packets belonging to the same flow. Simplification may degrade emulation accuracy. Behavior depends on packet size, such as fair queuing. If you have a mixture of different packet sizes, it enables the emulator to achieve high throughput, as I will discuss in more detail later. Each abstract packet includes just the information needed by the emulated resource management scheme, such as the source, destination, and any custom packet header fields. For example, to implement priority queuing in Flexplane, each abstract packet must include the real packet's priority. Because communication between endpoints and the emulator occurs over the same network used to transmit real packets, it consumes some of the available network bandwidth. However, abstract packets are themselves quite small, about 12 bytes in a typical case. In addition, multiple abstract packets can often be sent together to the emulator in the same real packet. For example, when a single send or send to call on a socket requests many packets worth of data. Abstract packets are also efficiently encoded into real packets. When an endpoint requests several packets in the same flow, the flow information is not included multiple times in the same packet to the emulator. The result is that in our experiments, we found that communication between endpoints and the emulator required only 1 to 2% of the network's bandwidth. The purpose of emulation is to,
Does that mean this emulator can only support 50 to 100 clients?
how are you using
So
that?
if you're consuming 1 to 2% of the network bandwidth, and if you have 100 clients, then you're consuming 100% of the network bandwidth, right? Are you saying how did you measure that 1 to 2%?
That's the 1 to 2% is the amount of the ratio of the abstract packet traffic for communicating between the endpoints and the emulator, and the amount of traffic that's actually sent over the network with real data.
I see.
In the worst case, we're sending one abstract packet for each entity.
I see, okay. Okay,
Yeah, you can imagine having an emulator that has multiple NICs in order to scale up the
So
throughput
then-
available, if that's what you're concerned about.
right, so if you had a client sending at full blast,
Yeah,
it would, the emulator would be receiving an amount of traffic, it's about 1% of that traffic, right?
yeah.
So then if you had 100 clients sending at full blast,
Mhm.
then the link to the emulator would basically be full.
Yeah. So at that point, you would need to start adding multiple NICs to your emulator in order to scale up the amount of throughput it could support.
Okay.
Yeah. So the purpose of emulation is to delay and modify abstract packets just as they would be delayed and modified in a hardware network running the same resource management scheme. When abstract packets arrive at the emulator, they are enqueued at their emulated sources. They then flow through the emulated topology, ending at their emulated destinations. As they flow through the emulated network, they interact with other abstract packets. They may encounter queuing delays, require modifications from the routers they traverse, or be dropped, just as they would in a real network. Thus, the emulation functions as a real-time simulator. So one naive way to implement the emulator would be to simply use an existing software simulator, such as NS. However, this would run incredibly slowly. So instead, we implemented our own emulator, which differs from standard software simulators in two key ways. First, the emulator divides time into short time slots. The duration of a time slot is chosen to be the amount of time it takes a NIC in the hardware network to transmit the number of bytes represented by an abstract packet. Thus, in each time slot, each port on each emulated router and emulated endpoint can send and receive one abstract packet. Simplified emulation, scheduling each event, such as at a specific software simulator. The emulator only needs to ensure that each time slot, which can include dozens of these such events, occurs with the correct time. So in this way, Flexplane sacrifices a little bit of accuracy in exchange for running in real time. Second, the emulator only simulates the in-network functionality from the endpoint NICs onward. We assume that any endpoint support for resource management schemes, such as modifications to the endpoint TCP stack for DCTCP, are implemented at the real endpoints. By leaving this functionality to the real endpoints, the emulator runs much more quickly, and the results more accurately capture real network behavior. As soon as an abstract packet exits emulation, the emulator sends a response to the source endpoint, indicating how to handle the real packet on the real network. If the abstract packet was dropped during emulation, the emulator will instruct the real endpoint to drop the corresponding packet rather than sending it. Otherwise, if the abstract packet reached its emulated destination, the emulator will instruct the real endpoint to immediately modify the real packet if necessary and send it. Modifying packets before sending them is required for correctness for schemes whose behavior depends upon received packet headers. For example, in ECN-based schemes such as DCTCP, PUL, and deadline-aware data center TCP, routers set the ECN field in IP headers when congestion is experienced, and the recipient must echo this congestion indicator back to the sender. Similarly, in many explicit control schemes, such as RCP, PDQ, and PERC, receivers must echo information about the network, such as flow rates, back to the senders. To be a viable platform for experimentation, Flexplane must be accurate, meaning the results achieved in Flexplane predict those achieved on a hardware network running the same resource management scheme. To understand how Flexplane deviates from perfect accuracy, let's compare the latency in a packet, latency experienced by a packet in a hardware network to that of a packet in Flexplane. In a hardware network running a given resource management scheme, the latency of a packet is the sum of the one-way unloaded delay, meaning the one-way latency in an uncongested network, and the one-way queuing delay. In an identical network that implements the same resource management scheme using Flexplane, packets still experience the unloaded delay and the queuing delay, but these now occur in the emulated network instead of in the real network. In addition, packets incur an additional delay for the round-trip time to the emulator and back, for when the real packet traverses the real network, and for any queuing delay encountered in the real network. Our emulator uses kernel bypass, reducing the round-trip time to the emulator. The result is that, in practice, the latency in an unloaded Flexplane network is about 2.3 times the latency of a packet in a hardware network. Flexplane does not guarantee zero queuing within the hardware network. However, the emulation enforces bandwidth constraints, guaranteeing that there will be sufficient bandwidth available to transmit all packets admitted into the network to their destinations, and queues cannot grow indefinitely. In practice, we found that these queues remain small, about 8 to 12 microseconds when links are fully loaded. Flexplane exposes simple APIs to users so that they can write their own schemes. At the emulator, the implemented schemes are decoupled from. Users implement simple functions at the emulated routers, and the framework takes care of calling these functions at the appropriate times. Two C++ APIs. In the pattern API, which works for most schemes, users implement functions such as route, classify, and schedule. More flexibility than is available with the pattern API. For example, if they want to defer routing decisions and perform them together with scheduling decisions, they can instead use the generic API, which simply includes input and output functions to be performed at each time slot at each router. Flexplane also provides a C API for reading and modifying packet headers at the physical endpoints. For schemes that require access to custom header fields, such as priorities or rates in explicit control schemes, the user specifies how to copy these fields from the real packets into the abstract packets by implementing the prepare request function. Similarly, to modify packet headers after emulation is complete before a packet is sent out onto the real network, for example, to apply ECN marks, users implement the function prepare to send. To enable useful experiments, the emulator must support high network throughput. To achieve this, the emulator runs on a multi-core machine and uses additional cores to scale throughput with the size of the network. However, existing architectures for multi-core packet processing are ill-suited for the Flexplane emulator. For example, consider this two-tiered network topology. One common approach to packet processing is to run cores in parallel and to process each packet to completion on a single core. This is the approach taken by the software router RouteBricks and by the data plane operating system X. However, if the emulator used this approach, cores that process abstract packets traversing the same emulated network components would contend for the shared state of emulated routers and endpoints, limiting scalability. For example, if two cores simultaneously process abstract packets headed to the same destination in the same time slot, they will contend for the shared router state. Another approach used in the centralized packet scheduler FastPass is to pass packets down a linear pipeline of cores. To use this approach in the emulator, we could pin different emulated network components to different cores and pass abstract packets down the pipeline. However, this approach doesn't work either because different packets may access endpoint and router state in different orders. So for example, this ordering works well for a packet from source 1 to destination 8, but it wouldn't work for a packet from source 8 to destination 1. Instead, our multi-core architecture pins each emulated network to a core and connects them in a graph. Abstract packets then flow between these different cores via FIFO queues. With this architecture, router state is never shared across cores, and cores only communicate when they have packets to exchange with each other. To reduce the overhead of inter-core communication, Flexplane employs a couple of additional strategies. First, Flexplane maintains only loose synchronization between cores. Each core independently ensures that it begins each time slot at the correct time using CPU cycle counters, but the cores do not explicitly synchronize with one another. Second, Flexplane batches access to FIFO queues so that all abstract packets to be sent on or received from a given queue in the same time slot are enqueued or dequeued together. This reduces contention on the shared queues. And finally, Flexplane prefetches abstract packets before they're accessed on core. We implemented Flexplane by extending FastPass, a centralized scheduler for data center networks. The emulator is implemented using Intel DPDK for low latency access to NICs from user space. Support for Flexplane at the endpoints is implemented in a Linux kernel module, which functions as a Linux queuing discipline. We conducted experiments with Flexplane on a single rack of 40 servers in Facebook's data center network. One server was set aside for running the emulator. We used an MTU size of 1,500 bytes, and we disabled TCP segmentation offload so that Flexplane can control the transmission time of each individual packet. Our experiments focused on evaluating Flexplane in terms of three properties. How well does Flexplane predict the behavior of schemes already supported in hardware? Second, utility. How easy is Flexplane to use, and what forms of experimentation can it enable? And finally, emulator throughput. It provides sufficient throughput to support data center applications. To evaluate the accuracy of Flexplane, we compared its behavior to the behavior of hardware for 3 schemes that are supported in hardware today: Droptail, Red, and DC-TCP. In this experiment, 5 senders send bulk TCP traffic to 1 receiver. All schemes achieve very similar throughput for the bottleneck link. Throughput is slightly lower with Flexplane because a small amount of throughput is reserved for abstract packets. During this experiment, we also sampled the queue occupancies in the hardware switch and in the Flexplane emulator every millisecond. We found that for each scheme, the queue occupancies in Flexplane were similar to those in hardware. The most noticeable difference between the two is that the queue occupancies tended to be slightly lower in Flexplane than in hardware because of the effectively longer round-trip time in Flexplane. We also evaluated the accuracy of Flexplane in terms of flow completion time. We ran an RPC web search workload that includes a mixture of flows of different sizes. Request times were chosen by a Poisson process, such that the clients received a specified load between 10% and 80%. And we normalized the flow completion time for each flow by the flow completion time of a flow of the same size in an unloaded network when flows are requested continuously. This graph shows the results of this experiment for DC-TCP for small flows on the left and for large flows on the right. We also ran this experiment with Droptail. Across DC-TCP and Droptail, Flexplane predicts the average normalized flow completion times to within 2 to 14% for loads up to 60%. For higher loads, Flexplane's accuracy decreases slightly, but remains within 18% for small flows and 24% for large flows. Yeah?
When you measure flow completion time, do you measure it from like the packets in the real hardware or from the emulator?
In the real hardware.
How different is the flow completion time you get from the emulator? When the last packet.
You mean, so when you say measure it from the emulator, you mean look at the completion time of a flow just within the software emulator?
Yeah, like when the last abstract control packets received.
We didn't measure that, so I don't know what the answer is to that.
Okay. But that can that be similar or it should be close?
It should be similar. The only difference should be, it should be basically the flow completion time that you measure in the hardware minus the extra time to talk to the emulator and to send the last real packet across the network.
And the time in the end host?
Yeah, and the time of the end host.
How different is the time in the end host if you're using the emulator versus if you're not?
What do you mean?
Is there additional latency because you have to send some packets to the emulator from the end host?
Yeah, so that's sort of that fixed added delay you see at the beginning when you have to send the first abstract packet to the emulator and get the response back.
Okay, so this that fixed it.
Yeah. Yeah. So these graphs also demonstrate behavior that is not visible in software simulators. For large flows, the normalized flow completion time at the lowest load are close to 1. This is what we would expect. For small flows, however, the normalized flow completion times remain above 2, even at the lowest loads. Here is due to the properties of real endpoint network stacks. In real endpoints, application layer latency depends on the rate at which packets are sent. When packets are sent at a high enough rate, the latency decreases significantly. For example, in one network, the ping latency dropped from 77 microseconds to 14 microseconds when pings were sent every 50 microseconds instead of every 2 milliseconds. Behavior across different network stacks and NICs. What this means for this experiment is that at low load, packets aren't requested frequently enough to attain the ultra-low latency that is possible when they're requested continuously. And the normalized flow completion times don't approach 1. Yeah?
Do you know why that is?
I'm not sure of the exact details. I think it's due to some something in the operating system that gets more efficient when you're processing a lot of packets. I don't know what the specific mechanism is. Yeah. So this behavior doesn't occur with large flows, which send enough bytes to fully occupy the NICs. This is an example of behavior that is hard to accurately model in simulation, but it's automatically captured with Flexplane. We've implemented and experimented with several different resource management schemes in Flexplane. We found that most schemes required only a few dozen lines of code to implement using the Flexplane APIs. For example, we implemented hull in 60 lines of code. pfabric required significantly more code than the other schemes because it does not maintain packets in FIFO order between the NQ and DQ stages. So 170 lines of code were used to implement custom queuing. This shows the main source code used to implement the queue management scheme, DCTCP, in Flexplane. For each abstract packet that arrives at a DCTCP queue, Flexplane calls this enqueue function. Abstract packets are stored in a packet queue bank, referred to as mbank here, between when they're enqueued at the router and when they're dequeued. This code first gets the current queue length from the queue bank. It then checks if the queue is already at its configured capacity. In this case, it drops the abstract packet and returns. Otherwise, it checks to see if the current queue length exceeds the marking threshold. This is the parameter K in DCTCP. If so, it marks the abstract packet by setting the ECN bits in its header to indicate congestion experienced. Once this is done, the abstract packet is enqueued to the queue bank. Abstract packets will be dequeued in FIFO order by a schedule function. Flexplane enables several forms of experimentation that aren't possible without it. First, we used Flexplane to compare the performance of different resource management schemes on a specific workload. In this experiment, we used an RPC-based workload that consisted of a mixture of short, high-priority requests and long, low-priority requests. Request times were chosen by a Poisson process so that client NICs were receiving at about 60% of their maximum throughput. This graph shows the trade-offs that different resource management schemes make. The x-axis shows the flow completion time for the long, low-priority flows, and the y-axis shows the performance for short, high-priority flows. The axes are flipped so that better performance is up and to the right. For this simple workload, priority queuing achieves the best performance. Droptail performs well for long flows, but poorly for short flows because it allows large queues to build up in the network. At the other end of the spectrum, hull demonstrates the opposite behavior. This is because hull uses phantom queues to cap link throughput at slightly less than link capacity. This slows down the long flows, but allows the short flows to achieve good performance. This experiment demonstrates how Flexplane enables users to compare the performance of different resource management schemes in a real network, even those not supported by routers today, such as pfabric and hull. We also used Flexplane to evaluate how new resource management schemes affect the performance of an unmodified application, distributed application that uses other resources besides network, such as CPU. For this experiment, we ran two different Spark applications using Flexplane to implement DCTCP with a small task. Both DCTCP and hull yielded small improvements in completion time over Droptail. In contrast, the coordinate descent application, which primarily sends large bulk data transfers, experienced a slightly higher completion time with DCTCP and significantly higher completion time with hull because of these schemes' more aggressive responses to congestion. Both of these Spark applications spend the majority of their time performing computation. It would be very difficult to accurately model them in a software simulator and to conduct this experiment in simulation. Yeah.
Have you compared how these? Have you looked at how these results compare with people who emulate, who've simulated Spark workloads where they just take the flow sizes and arrival patterns?
That's a good question. I haven't compared to that, but that would be an interesting thing to look at. Finally, we measured the maximum sustainable throughput of the Flexplane emulator. In this experiment, we used 2 cores on the emulator machine to generate the workload, and another 8 to run the emulator. With all 10 cores and a topology of 7 racks, the emulator achieved a total throughput, aggregated across all routers in the network, of 761 gigabits per second. Thus, the emulator could support a network of 224 servers, each sending at an average rate of 2.5 gigabits per second. We also evaluated the throughput for different emulated network topologies. All topologies included one aggregation switch connecting 2 or more racks of machines, such as this topology. This graph shows how throughput scales with the number of cores used in the emulator. The smallest configuration requires 3 cores, one for the aggregation router and one for each top of rack switch and its endpoints. In this experiment, throughput falls short of linear scaling based on the throughput of a single router and its endpoints. To understand why, we measured the throughput of topologies with up to 8 isolated racks of servers, with no communication between racks. The throughput in this case is much closer to linear scaling, demonstrating that the shortfall from linear scaling in the case of connected racks is primarily due to inter-core communication with the core running the aggregation switch, rather than contention for shared resources such as the L3 cache. The throughput results on the previous slide were all for the scheme drop-tail. We also evaluated how throughput changes with more complicated resource management schemes. This graph shows the maximum throughput achieved for a single emulated router across the 7 different schemes that we experimented with. BCTCP and drop-tail achieved the highest throughput of about 120 gigabits per second. The most complex scheme we implemented, pFabric, achieves 85 gigabits per second, about 29% less throughput than drop-tail. Overall, the Flexplane emulator significantly outperforms software routers in terms of throughput. For example, the RouteBrick software router provides 35 gigabits per second of total throughput with 32 cores. If we compare throughput per clock cycle in order to normalize for differences in clock frequency and in the number of cores used, we see that the Flexplane emulator achieves 81 times as much throughput per clock cycle as RouteBricks. This is because the Flexplane emulator only processes abstract packets, allowing it to maintain a small memory footprint. All of the memory used in this experiment fits in the 30 megabyte L3 cache shared by the 10 cores. In contrast, RouteBricks applications access 400 to 1,000 bytes from memory for each 64-byte packet that is processed. In summary, I described the idea of full network emulation in a center and presented Flexplane, use full network emulation to provide accuracy, flexibility, and high throughput, and to enable experimentation with real applications such as Spark and real networks. Thank you, and I'm happy to take more questions. Yeah.
So you mentioned that the memory footprint of the emulator falls within the L3 cache.
Yeah.
Would that limit your scalability if you try to scale to, let's say, 20 or 30 cores and larger networks?
So if you're scaling to 20 or 30 cores, you're probably running across multiple sockets now, and each one will have its own L3 cache. So there's definitely a lot of new challenges that we didn't focus on in this work once you start trying to scale across sockets, but you would have additional cache available in those sockets. Yeah.
Sorry, this is obvious, but you mentioned that it's about 1 to 2% in network usage to run the emulator. Is that net of the gains you'll get by the fact that you won't actually have to run the actual packet when it realizes it's going to be dropped?
I think that includes the fact that you do drop some packets. But I mean, I would imagine in many cases the number of packets dropped is pretty small, so that wouldn't significantly impact your numbers. Yeah.
So the workload that we use is the web search workload, which is pretty heavy tail. Have you ever tried to use any other kind of workload that is more kind of in contrast to heavy tail, lots of short messages, and that 2.3 RTT overhead that the Flexplane will have will actually cause the system not to behave correctly?
Yeah, that's a good question. We didn't look at any other, I guess we also looked at like a data mining workload, the other one that's used by the DCTCP paper, and we didn't see any like significant differences in the results. But we haven't looked at a workload that takes us to the extreme with much smaller flows. Lavanya?
Is it possible to use the emulator, just the emulator as a faster version of NS or ONNET?
Yeah, so that's a good question. In theory, yes, but you would still need to have something actually like generating your workload, and you would need to have some component that simulated the endpoint, since the emulator doesn't simulate the endpoint behavior. So once you start doing all of that, I'm not sure if you would actually see benefits. At that point, it might just make sense to run like Flexplane in its entirety. But you could, in theory, set up like something like Mininet or something to try and run the endpoint components and then connect it to Flexplane to run the actual simulation of the network internals.
Okay. What would be the scalability bottleneck then, the inter-CPU?
So if you were trying to run all of that on one machine, I would imagine that just trying to simulate or trying to emulate the actual endpoint software would become like a significant limitation.
Like if we then want to emulate the entire software, but we just have a program that's generating just the packets, I mean, not going through any stack or.
I mean, you could do that, but for for most experiments, you're going to want to have the real endpoint software stack as part of the experiment, right? Yeah.
So in the two slides before this slide, there was this one. Sorry, the one that shows the throughput of different. Yeah. So do you know why PFAB around 70?
I mean, so pFabric is less than because it's a much more complicated scheme to implement. When you have a packet, instead of having just a FIFO queue, you have to insert it into the right place based on its priority. So that's it's a more complicated operation, so it limits the throughput of the emulator.
Oh, it limits the throughput of emulator. Actually, it's just the throughput of emulator, not the actual throughput of pFabric.
Yeah. This is the throughput, like just benchmarking the emulator itself.
Okay. Yeah.
All right, thank you very much.